Okay, hey, let us get started with today's lecture. So I would like to just go over again this condition. There are a couple of examples that I would like to discuss with you. I guess you must have already seen basic stuff when Korhan actually taught last week, but there were a couple of examples that I wanted to cover myself. So I would just say this is a review for conditional expectations. Right? So you remember how we defined the conditional probability of an event B given that an event A has happened, right? So this in the first place makes sense only if probability of the event to which you condition, right? And in that case it is defined as the quotient of what? The probability that A and B happens at the same time and probability that A happens, right? If probability of A equals 0, namely if event A cannot in fact happen, right? Then we could just put whatever number you want. So we basically say it is undefined. So we don't really care what happens in that case, right? If we have two discrete random variables x and y, we can use this basic definition to define or to actually produce the conditional probability mass function of random variable x given that y equals a fixed number, right? So in this case, let's say the conditional probability that x equals little x given that y equals little y, right, will be, right, sometimes we denote this, right, by this notation, right? X and y are two possible values that these random variables can take. And we define this, right? So here in this definition, you take event B as the event that x equals x, little x, and you take event A as the event that y equals little y, and then just you apply this definition, and then that will give you what? This is the ratio of the probability, unconditional probability that x equals little x and y equals little y divided by the probability that y equals little y, whenever the probability that y equals y is positive, right? And just leave it as undefined, right? Otherwise, namely, if y cannot take value little y with some positive probability, right? And let's look at an example where we can actually first of all, see how the conditional expectations arise, and then use the basic definitions to solve some interesting problems, right? In many problems, conditional probabilities are given. They are not the ones that we are usually asked to find. People usually find it easier to basically specify the conditional probabilities, because if you fix part of information, if you know a little bit more about how the world is supposed to go forward, then you can say actually more about the likelihoods of certain events. Unconditional probabilities are usually more difficult to really identify themselves right away. If you know more about the conditional probabilities, you can just gather all those information to find whatever unconditional probability you want to calculate, right? So I don't have much information about where I take this example, but let me just read the question. Most probably this is also coming from your textbook. Okay, number of customers, okay, who enters, right, to a shop on a typical day has Poisson distribution with a given mean lambda, right? So it's you pick real, I guess, right? Was it real? So the number of people who enter there on a typical weekday, let's say, weekends may be different, right? Follow a Poisson distribution with mean lambda. Every customers make a purchase only with some probability p, right? So not everybody goes there to buy something. Maybe they cannot find whatever they want. Maybe they don't like the price, or maybe just they are spending their day just to look around, right? So only with probability p, a given customer makes a purchase, and independently of every other customer. So they don't look around, and none of us, I guess, make a decision of buying something or not based on how many other people are buying the same stuff. And if it is, okay, I'm not going to elaborate too much about it. Then, well, what is the question? We would like to know the distribution of the number of customers who actually purchase something on a typical day, right? So we know how many customers on average comes in. We also know the distribution. And we know that independently they make a decision about whether they buy something or not. And then, well, if we own the store, right, we would like to know actually how many, on average, on a typical day, customers will really make a purchase. And that's the question, right? So we did not specify, well, it is our task to first model the problem, right? In this case, task is easy. We only have to pick up the right random variables and then just use them to decode the information given by the question, right? So I pick X to denote the number of customers who enter the store on a typical day, right? The number of customers who enter the shop, right, on a typical day, right? And we are also interested in the number of customers who, right, who enter the shop and make a purchase, again, on a typical day, right? Right? So these look like quite natural to define. And what do I know? What is, first of all, I want what? So that's important. I would like to find out, right, what the distribution probability mass function, right? So obviously, number of customers, right, who will make a choice is a discrete random variable. Therefore, we are interested in the mass function of random variable n, right? But I also need, in order to solve this problem, I also need to just find out what is given to me, right? What do I know? In this case, first of all, I know the distribution of random variable x, right? Number of customers who enter the shop on a typical day, according to this statement, has a Poisson distribution with mean, right, lambda, that is given. And then, what does it say? So we have to find now the right way to formulate the following statement. It says, every customer, right, makes a purchase with some probability p, independently of the others, right? So how can I represent this or write down this piece of information using these two random variables, right? How can I do that? So maybe I should first write a statement, right? So then we'll see how this is going to be converted. So every customer, right, we should say in the shop, right, makes a purchase, right, with the same probability p, which is a number that is given to us, right, with the same probability p, independently of other customers, right? So this sounds like actually there is a Bernoulli experiment going on, right? And yes, success or failure. It is a success for us if a given person makes a purchase. It's a failure otherwise, right? And these Bernoulli experiments are independent of each other, and they all have the same success probability, that they will make a purchase with probability p, right? These are, in fact, true only conditioned on the number of customers we have in the store, right? If there are nobody in the store, so then none of this really make any sense to us, right? So in fact, actually, this also gives us a hint about what the distribution of n, right, number of customers who enter the shop and make a purchase should look like. Now, for example, the probability that n equals little n, right, if you condition on the total number of customers who are already in the store, right, should be what? According to this statement. Now, if you are told, right, for example, there are exactly X customers in the store, then it is like you are conducting, right, as you are pondering, thinking how many customers will be buying or will have made a purchase, what you are actually asking to yourselves, well, there are X Bernoulli trials currently going on, results of which are all independent of each other, and any one of which will result in a success with the same probability P. Right? And you are interested in what? Total number of successes. In this case, actually, you are asking to yourselves, right, the probability that total number of successes equals n, given that I am currently conducting exactly X Bernoulli trials. Right? So what should the distribution look like? Binomial. Right? Because what? There are, well, X experiments being conducted right now. Exactly n of them, you want exactly n of them to be successful, right? And since all these experiments, right, conditionally independent of each other, right, and n of them will result in a success with the same probability P, and the remaining X minus P of them will should result in a failure, right, with probability 1 minus P. We multiply all together these things because, yes, that's a good point, because they are independent of each other, right? That's the problem when you are while you are, well, you write while you are talking. Okay, that's great. So you are awake. That's great. All right. So do we agree with all this? Huh? This is of course true as long as n is a number, right, integer between 0 and at most x, right? And well, of course, you also want x to be a non-negative integer, right? Okay. Otherwise, this probability is either undefined or I just don't care. You can just assign 0. Perhaps in certain cases, it is going to be 0, right? Now, so that's exactly what we are. But this is the most or almost all information that you can extract from these two things, right? So we know unconditional probability distribution of random variable x, and we now also found out what the conditional distribution of number of customers who actually make a purchase, right, given the total number of customers that are currently in this store, right? And what is this? What we really want to calculate is, in fact, the unconditional probability that n equals little n, right? That's what we understand, or how we define a probability mass function, right? What is the probability, unconditional probability in this case, right? That there will be n purchases on a typical day, right? So all we have to do is just think a little, first of all. So the event n equals little n, right? Right? So I assume that n just a non-negative integer, right? So we are looking, of course, the interesting case. If it is not, the probability of this event, of course, equals 0, right? So before we worry about the probability, how is this event related to, right, to random variable x? Well, at any day, while there are exactly n customers who actually make a purchase, there must also be exactly x customers in the store, right? So x can be anything, but for this to make really sense, right, x should be at least as large as the number of customers who actually make a purchase, right? So this is going to be like this, right? Well, what is wrong if you put 0 here? Well, nothing is wrong, because in those cases, when n equals, for example, 4, when this is 0, this event, right, the joint intersection of two events is going to be what? In this case, 0 means, in terms of sets, empty. We haven't come to probability yet, but the intuition is exactly right. So nothing wrong if you just don't really pay attention to the detail and just write like this. So you don't make a mistake. But then we will only be interested in the sets which are non-trivial, right? The empty set, we know the probability is 0. Why should I care, right? So you know that you only look at, right, you have to figure out the probabilities for those events which are not empty, right? So that's exactly this combination that I have to worry about, right? So we are clear about this, right? It's just a logical statement. In order to have exactly n customers making purchase, you first of all have at least n customers in the store, right? And this can be any number between n and infinity, right? I write each case separately because I would like to just write this in fact in terms as the union of disjoint events. For different x's, these sets are disjoint, right? So these are all, well, I should say pairwise disjoint for different x values. Why should I care about this? Well, when you want to calculate now the probability, then there was this important axiom of probability that says whenever you want to calculate the probability of an event, or whenever you want to calculate the probability of the union of disjoint sets, it is given as what? The sum of the probabilities. If the sets are not disjoint, then we cannot just sum them, right? We have to then worry about how many elements you actually counted twice. You remember the Dagli formula? You must have also done in your homework, I guess. Right, so in this case, since these are disjoint, then probability is, of course, the probability of the union. But since this is union of disjoints, countably many disjoint sets, it is given as the sum of the individual probabilities. Okay? So now x goes from n to infinity. Right? Okay. Then how can I find this joint probability distribution? Well, there, I guess we are ready to use these two pieces of information. As I said, it is usually difficult or perhaps also unnatural to specify joint distributions simultaneously. People usually find it a lot easier to find actually simpler units. Like x alone has this. It is easy, so you will just put somebody sitting over there, just count number of people who are entering the store, right? And then here, I don't know. So this, for any given person, probably you can, now that you have the loyalty cards, for example, people actually give them, hoping that they will get a discount for that, right? But in the meantime, what the store is really doing is they just actually profile you. Then what kind of products you purchase, how often you purchase, things like that. So for any given customer, then they are likely to figure out this probability as well. So these are easier to calculate or easier to find information. And we will now use to figure out this apparently more difficult quantity. But here we basically use what? We just remember what the conditional probability, how the conditional probability was defined, right? So we can condition on, well, not this one. I will just write the other one first. Maybe it would be okay, I guess. So this times the probability that n equals little n given that there are exactly x customers, right? So I can write this like this because that comes basically from the definition of this one. So you remember this was defined as what? Joint probability of these two events divided by this probability, right? I just reversed that because these are given, this is not, right? Now I will use that. And, right, do we have any questions by now? Okay. Now, what is this? Now you remind yourselves what the probability mass function for a Poisson random variable looks like, right? It is, if the rate is lambda, huh? Not too fast. So lambda times, okay. This x. Now, this looks like, to me, actually the density function of an exponential, if x is the variable. How about this? Huh? Okay. We have to do more exercise in order to not forget this at all. So this is gonna, you will start seeing this in your dreams, actually, after a while. We will do so many exercises with these guys. They are quite fundamental for us. Right? Is this right? Lambda to the power x times e to the minus the rate. You divide them by x factorial. I guess what really causes it, usually we tend to use integers to pick, we pick integers actually to denote a particular realization of random variable. When you see an x, you tend to think like it is an exponential, a continuous random variable in the first place, and therefore, I guess the wrong part of your memory just get invoked. So that is that. And well, we already wrote this. Actually, I shouldn't have done this. So we could maybe inverse, it is better to write. So what the conclusion should have been here, right? Given that x equals little x, right? There are exactly n x customers in the store, right? The random variable n, right, which is the total number of purchases made on the same day, right, has conditionally binomial distribution with, well, the binomial distribution has how many parameters? 2, right? They already appeared here. Which ones? Like x and p in this case, right? With parameters, well, now the parameter depends on the value of the previous random variable, right? Parameters x and p. Unfortunately, there are not, I mean, people, I mean, we know what they mean. They don't really give names when they define, but x is like what? Number of experiments in this case, and the p is the success probability, right? Now with what probability you get the success. Okay, so that's great. So this has a name. So conditionally it has binomial distribution with parameters x and p. Now, and this now equals, just as I wrote over there, x choose n times, right, the p to the power n times 1 minus p to the power x minus n, right? Right? Okay. Now, is this likely to simplify any further? Huh? Have you seen this example before? Huh? Well, this is an important result, actually. We will also see alternative derivation later when we discuss Poisson processes. Okay, let me just copy that here while I make, well, replace some of the quantities with what exactly they mean. So this is a sum from x equals n to infinity, right? Then you have lambda to the power x divided by x factorial e to the minus lambda. We could have taken this outside, but let's just take care of that later. P to the power, no. What do I have? N choose x, what is that? N choose x is x factorial divided by x minus n factorial times n factorial, right? That's that. Then you have p to the power n times 1 minus p to the power n minus x, right? Okay, I only replaced n choose n with whatever that means. I did that because there will be some cancellations, right? And you look at this, right? Whatever doesn't depend on x, we can just take them out, right? What do I have there? For example, e to the minus lambda, we can take that out. This one, n doesn't depend on x, right? So the sum is over x, right? Even though the bound starts from n, but that I don't really care. P to the power n, we can take that out as well, right? And have I made a mistake over there? No, that one is correct, but this is wrong, right? This is supposed to be large minus small, right? And I could have taken n, but let's just leave it as it is. So this now looks like what? So this is lambda to the power x, right? Divided by x minus n factorial, right? These are gone, and 1 minus p to the power x minus n. And we can just adjust the bounds, right? If you subtract minus n, right, then we have to add minus n. So subtract minus n, so this is still minus infinity, right? So this is going to be plus, and this is going to be plus n, so they cancel, right? And you will have plus n here as well, they will cancel as well, right? And then what do you get? So anything that doesn't depend on n can go out, right? So you have, okay, let me just write, so even I can make a mistake, even though I did this exercise so many times. Okay, here you have what? Lambda to the power x plus n divided by x factorial times 1 minus p to the power x, I guess, right? So this is lambda to the power n. We can just take that out, right? So lambda to the power n, let me just erase this, right? we have something like this, right? So they have the common power x over there. We can, why don't I just write them together? So this is like lambda times, first of all, 1 minus p, and then to the power x. We can do that, right? Right? And then you ask to yourselves whether there is any compact way to write this one. Huh? Does this look familiar from calculus? So this is like x or, huh? Exactly. So I changed the variables here though, but it is e to the y, e to the power y. So this is, say it again, e over x. X is a dummy variable. So x should not appear in the formula. Whatever is sitting under the, well, whatever is in the, yes, exactly. So this is not working anymore. So this is e to the, if you have forgotten this, it doesn't matter. Now you know what it is, right? So this is exactly whatever is sitting here, raised as a power of exponential, the number e, right? And then we can actually bring all these things together, right? There is another exponential function here, right? E to the minus lambda. One of the lambdas will cancel, right? This lambda minus lambda will cancel this lambda. And you will have minus lambda p, right? E to the minus lambda p. You of course divide by n factorial, right? And then you have what? Lambda times p, right? The same number which is in the exponent to the power n, right? And we said this is true for any n, 0, 1, 2, whatever, right? Right? We not only got a simple expression instead of a summation, but also a name for this one, right? So n, therefore, has what kind of a distribution? Poisson, exactly. Now we knew that the conditional distribution of n given x has binomial, well, unconditionally, right? If you don't know how many customers there are in the store, unconditionally, right? At the beginning of the day, let's say, you haven't seen anybody yet, right? By the end of the day, people will come and go. But before that, all you can say is the distribution of this, right? And according to this, it is what? The Poisson with rate or mean lambda times p, right? And we could justify this answer partially, right? In the following way. So according to the problem, right, we said x has Poisson distribution with rate lambda, and lambda being the mean of Poisson distribution. We know according to this, on the average, right, there will be lambda, right, customers visiting the store, right? And if this is true, then that means that only p fraction, right? Only p is a number between 0 and 1, it is a fraction. If it is 0.3, for example, you know that 30% of them will make a purchase, right? Only p fraction of them, right, makes, or we expect only p fraction of them to make a purchase, right? And then you are interested in knowing the average, on average, how many customers will actually make a purchase. You will take, well, the p fraction of lambda, in this case, which gives you lambda times p, right? And it sits here. So n, in fact, has mean lambda times p. We know that, right? It is a lot more difficult, you need to just know more in order to justify why it should also have a Poisson distribution. Here we directly derived it. Later, when we introduce what the Poisson process is, then we will be able to say immediately that the n has to have actual Poisson distribution. Now we don't lack that information, but that still has to come, right? But then I will remind you when we come to that point that we actually did the exercise and we know that answer is consistent with the argument that we will have given at that point, right? All right. Do we have any questions? Right? Okay. So the important part of this was like you were given any information which was hidden. It was not like formulated like, okay, the conditionally on the number of customers, any customer has will make a purchase with such and such probability. They don't say, they don't write like this, right? So you have to be careful, and you should actually interpret what is really given and what is not. Whether these probabilities are actually unconditional or conditional probabilities, right? Here it was not that difficult. So you look at it, every customer in the shop, it means that that person has to be first of all in the store, right? For all, among all people who are already in store, what can you say about the distribution of who made actually a purchase? That's in fact the conditional. They are actually telling you some information about the conditional distribution rather than an unconditional distribution, right? So that's the key. The rest is just math. You may or may not remember some details. We don't care. So I'll remind you what part of calculus you will need to remember, right? So that part should not scare you. I know that the students are usually scared when they see integrals or products or exponential functions. And probably we don't care such things. There are more important ideas. You can just go back and just remind yourselves, and I'll help you remember them as well. Okay, such things are more important. If you are given a wordy statement, completely in English or Turkish, right, whatever your favorite language is, right, it is more important for us to be able to take this statement and being able to write like this, right? So we'll do exercise, we'll see examples of this kind in this class. Of course, we have to also deal with this ugly mathematics as well in order to produce an answer, right? That's secondary. Okay, so we said, okay, here was the definition, right? I said conditional probability was defined like this, and then we usually in class give definition for conditional expectation. In fact, they are the same. So we actually force our students to remember two things as though they are different, but they are not. We could have actually easily started with this. If you are given a random variable x and an event a, and if you want to define what is on average the value of x, if you are also told that event a has happened, right? Like here. So here, what is the probability of an event b, given that event a happened, right? Quite close, but you can now forget about this and remember all the time only this one. So we will define this thing as, again, a ratio of two numbers. In the numerator, you will have the unconditional expectation of random variable x on the event a. Right? So this notation no longer scares you, right? Because we already introduced indicator random variable. So you have a Bernoulli random variable multiplying another random variable, and then, well, the multiplication is, of course, is itself a random variable, so you can talk about its expectation. So you take that expectation, and then you divide by the probability of the event sitting here. Right? Now, since you divide by a number, you better make sure that this number is positive. Otherwise, you go through lots of trouble. So we don't want, we would like to avoid all of them. So we put it as a definition whenever the denominator is positive, and again leave it undefined if that is not the case. Right? Right? Now, this is a lot more useful than that one. You will see. We will do a few examples also. And I also find actually this is easier to generalize to other cases as well. But as I said, this is actually a special case of that, to see that here, see, this is true for every random variable x and event a. Right? If it is true for any random variable x, then I can just take as x one of the simplest random variable, which is what? A simple random variable is which can take only at most two values, right? Well, like an indicator random variable, right? So, right? For example, take X as the indicator of event, the same event B on the left-hand side, right? So I'll assume that the probability of A is positive, then look at the case, or calculate the conditional expectation of a Bernoulli random variable, which is in this case, right, the indicator of B, given that event A has happened, right? Well, if definition is this, then this becomes what? Indicator of B times indicator of A, right? Now, unconditional expectation, that's easy, unconditional. If you don't know, actually things are easier to explain, I guess. There is not much to explain at all, right? So you have this expression, you have to evaluate this expression. But how can I rewrite this one? Two indicators multiplied with each other. What is that? This is actually one indicator of B intersection A. Exactly, right? And then you have what? Expected value of an indicator of some set. In this case, it is just the intersection of A and B. What is the expected value of a Bernoulli random variable? Right? It is a Bernoulli random. Success probability. What is the success in this case? If A and B happen at the same time, right? So the success probability of this Bernoulli random variable is what? Probability that success happens or A and B happen at the same time, right? So therefore this is the same as probability A intersection B divided by, I don't do anything with denominator, it's just plain, it sits there till the end of this game. Now this is what? This is exactly the definition of what? Conditional probability of B given A, right? That's exactly what we did over there, right? So then you can safely forget about this and always remember this one. Always remember this one, okay? Okay? And as I said, we like this formula very much because conditional probability is written in terms of an unconditional expectation. Well, conditional expectation is written in terms of an unconditional expectation, right? And it goes back and forth, of course. So be depending on which part of this equation is given to you. Now we can now use this one to look at this formula. So if you are given a function g, and if this is first composed with random variable x, and then you are asked to evaluate the conditional expectation of this given, for example, a random variable y equals y. Right? So I'll make life easier by assuming that x and y are discrete random variables. For continuous random variables, we have an analogous formula. It is only technically more difficult looking, but otherwise the idea is the same. In fact, we use the formula for discrete random variables to argue that you should expect the same thing for continuous random variables. So let us look at this. Does this look in any way to this expression? Huh? If you want to make this look like this, you have to identify, right, different parts with different similar parts in the other expression. So y equals y. Well, it is in an event, actually, right? So this is itself is like an event A, right? Here, you condition on this. Here, this is true for any x and y. And if you are given a random variable x, if you compose x with g, you get another random variable. Maybe you would give another name, right? It is like a random variable 1, right? So you are in fact asked to calculate what? The conditional expectation of random variable y given an event A. So if you remember this, then it is not difficult to derive this, to find this, right? How do you do that? Well, you already see this. So I am again looking the case when this probability, namely y equals y, is positive, right? If it is not, there is nothing to define anywhere, right? For that particular case, so you pick a small y for which this is positive. Now I would like to know what this is. Then you have to use this, which says us that in order to calculate the conditional expectation, you first calculate the unconditional expectation of random variable y on the event A. But y was, by definition, G, right, composed with random variable x on the event that, on the event A, which is the same as saying y equals y, right? So instead of writing A, I just remind myself what the definition was, right, for A, right? And now you don't forget dividing by the entire expectation, right, by the probability that y equals 1. So that's that, right? That's that. And then, so this is big X, right? So it is a random variable, right? And now we have to find, well, we have to evaluate this one. This is already given, so we cannot do much about it, right? What happens here is, okay, so if X is a discrete random variable, right? So you can write this thing like this. X is going to take one of the values that random variable X can take, right? So X will be one of these numbers, little x, right? When X equals little x on that event, right? G of X is of course going to be G evaluated at little x. Does this make sense? I'm just talking actually pure logical stuff, right? So this is a mapping, right? So if you know the value of little x, so that you will know what the value of this thing. A priori you don't know, but all you know that x is going to be one of these little x's. So on the event that little x equals little x, G of capital X is going to be G of little x, right? What we are doing is actually you have this sample space, and you know that on some parts x equals 0, on some other parts x equals 1, right? And things like that. And G of X was what? A mapping of this set to the real lines, right? And then you say, okay, if my omega falls here, namely if, well, there will be also x equals little x. If my omega falls here, then on that set, of course, I have every right to replace this capital X with whatever that little x is, because the value, the realized value of x is then going to be little x, right? This is also a simple but very powerful technique. So we will be using this also a lot, right? Writing a complicated function in terms of what? Indicator random variables. What is this? There is nothing random here anymore, because this is a number. For all possible x's, you will know what this is. This is 14, 17, because this is x evaluated at little x. What is really random on the right-hand side is this indicator random variable, right? So omega will be in some of this, in exactly one of these sets and not in the others in a particular realization, right? So when you take, right, well, when you take expected value, this is like the sum of the expectations of these indicator random variables multiplied by some known numbers. That's why this is useful. But here now, I actually need more than this, right? So we have to multiply, because I am interested in the expected value of this thing. We multiply with this indicator random variable as well, right? Before I take expectation. So you multiply with the same stuff, right? Both left and right hand side. And we again play the same game. Two indicator random variables multiply together. So this is nothing but one indicator random variable of an event which is the intersection of these two, right? You intersect these two events, and that's nothing but this, right? 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 And then I can just copy here what I just got, right? So this is nothing but what? The sum over all possible numbers that random variable x can take, g times little x times the indicator of the event that x equals little x and y equals little y. And then I divide by this. Okay? Okay. I can still simplify this expectation, right? This is what? Expected value of some numbers times some random variables. The sum of expected value of sum of random variables is the same as the sum of the expected values, right? I can interchange the order. And when you do that, there will be the sum going out. As we said, these are numbers. They also go out of expectation. Then you have the expected value of the indicator random variable of the joint event that x equals little x and y equals little y. And then you divide by, as before, by the probability that y equals little y. Right? This is like sum again. But now, what is this? Again, we are dealing with the expected value of an indicator random variable, or well, a Bernoulli random variable. And its success, well, it equals to its success probability, which is, of course, this. Right? And therefore, what do you have? And okay, we can just write in a more familiar version. So there will be, so we can divide all these numbers by this, which doesn't depend on x, right? So you have the sum over little x's, right? G of little x times what? The success probability, namely x equals little x and y equals little x at the same time, probability of that, and you divide by the probability that y equals little y. And you are basically done, right? So to calculate conditional expectation of x given y, you have to evaluate this, but in the meantime you realize that this was what we call the conditional probability mass function of x given y, which was denoted, well, which we denoted in this case by this formula, right? So this is g of x times the probability that y equals, no, right? We condition on y, so this is x equals little x given y equals little y. And you sum over all x, right? So this is given like a formula or definition in many cases, but in fact it is nothing but just an application of this one, right? So do I want you to remember this derivation? No. What do I want you to remember? Well, if you have a complex random variable like this, then you can actually partition it like this. So then you have to only use tools to deal with indicator random variables. Indicator random variables are the simplest guys, right? They can take only two values, not more than that. If you want to take expectation, you know that you only need to remember what the success probabilities. And for the rest, well, the sum of those random variables multiplied with a bunch of numbers that you already know, well, the sums are also just our friends in probability, because when you take expectation variances, we know that those formulas can actually interchange orders. So if you then know how to deal with the sums of Bernoulli random variables, then you know how to calculate many interesting stuff. Okay? But by the way, this is also a short, well, formula. If you use it so often, of course, it also makes sense to remember the conditional expectation. Anyway, let's look at an example. See whether what I just said really is worthy learning. Now, this is a problem coming from your textbook. Is this coming well, I guess this is just the right time to give a break so that we can then start with a fresh mind. Right? I'll see you in 10 minutes.